Hello. What I'd like to do in this video is just kind of give you some tips or key hints on how to handle these synthesis and decomposition reactions that we've been practicing with. This is something that a lot of students seem to struggle with and get a little bit of trouble in mastering, or just kind of have a lack of confidence in. And I just want to kind of help you out with some key hints to kind of remember as you're trying to work your way through any of these decomposition or synthesis reactions. So just a few key hints. First, one of the things you'll notice in a lot of these reactions is, as you're working with them, if you've got the ingredients to make water, then water will probably be made as a product. And we're thinking, of course, here mostly of a decomposition reaction, where you're starting with one of these products and turning it into something on the left side as a reactant here, it seems like. Or the reaction's working in reverse. So as a decomposition reaction, if I have a hydroxide, then I have the ingredients to make water, and I'm probably going to make it. That's important to remember. So if you can look at the formula for the compound that you're given, and see the ingredients for water, obviously that's hydrogen and oxygen, then it'll probably be one of the products. And then figuring out the other product is usually easier from there. And I'll show you an example of that here in a minute. The same thing's true for acids too. Secondly, oxygen is very friendly. Oxygen likes to bond with everyone. Oxygen's a very aggressive element in terms of bonding and forming compounds. Plus it's very common, and so it's not difficult to find oxygen in just about every compound out there. So when we're working with these kind of decomposition and synthesis reactions, you'll find oxygen is all over the place. As you look at this table, oxygen is in all of these oxides, and obviously oxygen's in water, both places we see that. The only place we wouldn't necessarily expect to see oxygen all that much would be in the first row, the binary salts, but even there oxygen can be the nonmetal. So oxygen's really all over the place. And just remember that oxygen tends to bond with every element out there, and so we'll find it in a lot of our products of our reactions too. That can help you to remember what to make too. Finally, metals are parts of salts and bases. They're the first parts of salts and bases, but they're not found in acids really ever at all. And so when you're working on making a compound or trying to figure out what kind of compound I'm going to make in a synthesis reaction, remember that metals, when you see one, they're probably not going to make an acid ever. You can expect it's going to make some kind of a salt, whether that's a ternary salt or a binary salt, or even a hydroxide, which is just a sort, basically, of ternary salt. So let's go through, look at a couple of the examples from the packet, just to kind of give you a little bit of review, whether this is before you take the quiz or after. This is something to just kind of help you out and see a few of these that you maybe haven't already done. So let's look at number 19 as an example of a compound that maybe you can use these hints to sort of answer. First of all, number 19, you've got barium hydroxide. And what I'll always encourage you to do is, if you've got a formula's name or compound's name, to go ahead and write the formula for that compound, and it'll maybe help you to remember what the ingredients are, what the elements present are, and figure out how to go from there. So when I figure out barium hydroxide to be BaOH2, that's just nomenclature stuff, I can look at that and say, all right, which of these hints kind of works for me? I've got water present ingredients. Yeah, I've got hydrogen and oxygen in my hydroxide, so it's highly likely that water is going to be one of my products. So go ahead and fill water in on the other side. And then what else? Well, if I figure that hydrogen and oxygen coming out as water make one of my easy products to predict, remember the second rule here says that oxygen likes to bond with basically everybody. And I've got oxygen here, and it hasn't found a way to bond yet with barium. And barium's present, we need to take care of that. So in our second compound, barium's going to need to be there. And if we remember that oxygen likes to form compounds with everyone, well, put oxygen with it. And think through those charges, barium and oxygen, +2 and -2, so your compound will be barium oxide, and it's simply BaO. Barium is a metal. We need to take care of it in one of the products. It can't just disappear. So as we start to fill this in, barium's not going to form a compound by itself, but oxygen's going to jump in with it. Remember with decomposition reactions that you'll never really end up with just one element by itself unless you're taking apart a binary salt. Binary salts only have two elements in them, so when they come apart, you're going to have two elements by themselves. But any other compound, when you're taking it apart, whether it's a ternary salt, a base, or an acid like these that we'll work with in the examples, when they come apart, you're not going to get plain elements alone. You're going to get smaller, simpler compounds. Here we took barium hydroxide apart, a rather complicated compound, compared to our simpler results, barium oxide and water. Remember, if the ingredients to make water are present, go ahead and make it. We did that. And then remember that elements don't come out by themselves, and that oxygen likes to bond with everybody. Well, that makes this simple then. Barium was left. We had to take care of barium. We threw some oxygen in there with it because oxygen likes to bond with everybody, and we've got our two products. Remember those simple rules, and you'll be able to figure most of these compounds out rather easily. Let's look at number 20. 20 gives us aluminum phosphate, and it gives it to us as a formula, so we don't have to even figure that out. But again, let's think of the rules here. One, if water ingredients are present, go ahead and make water. We don't have hydrogen here, so we can't make water from aluminum phosphate. Jump ahead to the next rule. Oxygen likes to bond with everybody. Well, we've got oxygen here, and in almost all of these you're going to find you have some oxygen. The only ones you don't are the binary salts. So if we look at this and say if oxygen likes to bond with everybody, well, who's everybody here? Well, I've got aluminum. I'm going to have to take care of aluminum somewhere. So aluminum needs a partner in oxygen, and we have phosphorus, which needs a partner in oxygen. Oxygen bonds with everybody. In aluminum and oxygen together, that first product, what's aluminum's charge? Well, I go to my periodic table. It's typically a +3. I can figure out that since aluminum is usually a +3 and oxygen is always a -2, that my product will be aluminum oxide, and that's Al2O3. My other product, this is the trickier one slightly, I suppose, to figure out what are phosphorus and oxygen going to combine to produce. Well, it hinges on knowing what is phosphorus's charge in the original compound, because remember, typically these elements won't change charge as they go from one side of the reaction to the other. So if aluminum is a 3+, as it always is in a compound, and oxygen's a -2, which it nearly always is in a compound, what does phosphorus's charge have to be? Remember, compounds need to come out neutral. So if I'm looking at aluminum phosphate here as something that has to come out as a neutral overall compound, what charge do I need from phosphorus to make that happen? Well, I've got 4 oxygens here, and 4 oxygens at -2 for each one means I have a total of -8 on my oxygens here. Aluminum's giving me 3 pluses to kind of balance that out. I'm going to need to get 5 more pluses, or 5 more positive charge from the phosphorus in order to make my whole compound come out neutral. And that's what we're looking at in this top row here. So in order to make this come out neutral, phosphorus will have a +5 charge. Each phosphorus, in this case just the one phosphorus, will have a +5 charge. That +5 on phosphorus comes across to the other side too. And if we put that with oxygen, which is almost always a -2, I can make my compound to be P2O5, or diphosphorus pentoxide. That's the way you want to think these through. If you have the ingredients to make water, go ahead and do it. We didn't, so we skipped over that kind of hint. Number 2, oxygen likes to bond with everybody. So we put oxygen with the other parts of this compound, aluminum and phosphorus. We put oxygen with both. And then the last part was that figuring out phosphorus's charge in order to come up with the final formula for our phosphorus oxide, or in this case, diphosphorus pentoxide. Remember to think that charge through and bring those charges across to the other side of the compound too. Let's look at one more. This is number 11, dichlorine pentoxide. Now this is synthesis sort of going in reverse, but think about it the same kind of way in putting compounds together. And the rule that's going to help us out here is going to be the third one. But let's step through them. If the ingredients to make water are present, water will probably be made. Well, this is a synthesis reaction, so we're not thinking about it quite the same way, but we have water here, so it came out of our product on the other side. Oxygen bonds with everybody, and you see oxygen here bonding with both chlorine and hydrogen, so that kind of fits in too. It's done that. But the last one, let's look at that last rule. Metals are the first part of salts and bases, but not acids. How do I know that this is going to make an acid? Because it is. How do I know that? Well, the way I know is there's no metal present. As I look through this, I don't see any metal. Chlorine, that's a nonmetal. Oxygen, that's a nonmetal. Hydrogen, nonmetal as well. And so if I put these elements together and look at them as a group, I don't see a metal. I don't see any metals in this particular set of elements. And so I can't make a salt, I can't make a base, but I can make an acid. And that's really important to kind of come up with that process in your head. Knowing that I'm going to make an acid, we'll go ahead and put that name down as part of my answer. But I also need to come up with the acid's formula. Know and remember that all acids start with hydrogen as the first part, and then need some kind of a second anion part. What's that anion going to be? And that's the important part of our work here on this number 11. Well, it's going to need to contain the other elements we have, and that's chlorine and oxygen. Now, if you look at your ion possibilities, there's lots and lots of ions that could have chlorine and oxygen in them, at least 4 that we've talked about. So how do we figure out which of our ions with chlorine and oxygen in them is the right one? It goes back, like we saw in the last example, to the charge on chlorine over here, because we know oxygen tends to be -2. We know hydrogen tends to be +1 in compounds. What charge does that leave my chlorine to be? And if I look at my compound over here, I've got 5 oxygens with a -2 charge each. That's a total of negative 10, or an oxidation number of negative 2, I should say. And then on the other side, we need to have positive 10 in order to balance that out in terms of our oxidation numbers. 2 chlorines to get to positive 10 means that each chlorine has an oxidation number, or sort of pseudo charge, of plus 5. So chlorine's oxidation number of 5, oxygen's oxidation number of negative 2 go together to make each side come up with essentially plus 10 minus 10. Why is that important? Because this plus 5 is going to come across now to the other side and be part of our compound over here. Chlorine's plus 5 goes with it. The only question left to answer then is how many oxygens do I need to make this compound kind of work? Well, if I have plus 1 for my hydrogen and I have plus 5 for my chlorines, that's a total on this part of plus 6. And in order to make that balance out, we know oxygens are worth negative 2 apiece. How many oxygens will it take to get the negative 6 that makes this neutral? Well, hopefully you can look at that and say, I'm going to need 3 oxygens in order to make that happen. And there's my formula, HClO3. That looks like a legitimate acid that we could put a name to now. And remember, if you go to my sheet of ions or my list of ions in my mind, this is called chlorate. And again, our rules always being that chlorate, if it's got an 8 ending, will change to an IC ending as an acid. So chlorate becomes chloric, and we've produced chloric acid. Using those rules, using some of those guidelines to kind of help us, in this case, number 3 was the key. Without a metal present, that pretty much means it's going to have to become an acid when we're putting these 3 elements together. Our final one I'll just kind of run through really quickly is number 24. This is the simplest of all. When you have a binary salt, like potassium nitride here, it's going to simply come apart to produce the 2 elements that are present off by themselves. And so to do that, potassium nitride breaks apart to become potassium and nitrogen. But don't forget, nitrogen's on our diatomic elements list. That's probably the only mistake people would make with this one, and that's why I wanted to mention it. The simple ones, often people do really well with the tough ones, and then we get to a simple one and make a mistake they kick themselves for later. Don't forget nitrogen's diatomic, along with the other 6 elements on that list, our Cliff-Hoburn list. Keep those elements at the front of your mind on all reaction equations because they're very, very common in most equations. And then we just need to balance it. I haven't balanced any of these equations. I'm hoping by now your balancing is good enough to where you can handle that part, and I don't want to take the time to fill up this video with balancing equations as well. So keep those 4 rules sort of nearby. If the ingredients to make water are present, go ahead and make water. Oxygen's probably going to be found in whatever's left because oxygen likes to bond with everybody, and we saw that in some examples. And metals tend to be the first parts of salts and bases, but they're never found in an acid. So as we're working on these, if you don't have a metal, chances are you're going to be making an acid. The only exception would be one like these where we don't have enough elements to make a ternary compound anyway. So watch for metals. When you see a metal, it's not going to make an acid. And if you're lacking a metal completely, chances are there's an acid at the end of the rainbow for that one. So work on the others as you go. If you haven't finished that packet yet, do more of those when you have a chance. If you're doing the quiz today, good luck, and we'll go over it next time I see you.